Hello everyone. Today I'm pleased to introduce a new product that Direction is launching for medical fiber lasers. Direction is an indie semiconductor company. We were founded in year 2000. We are designing and manufacturing innovative photonic components with more than 170 employees. And the Direction office is located in Quebec City in Eastern Canada. Our products are based on three supporting technologies: FBGs, since the very beginning of Direction, integrated photonics, and low-noise semiconductor lasers. We are selling components for laser systems, including high-power lasers and ultra-fast lasers, for optical sensing, and for communication. Today, the focus is on a new product in the high-power family here. Our new product targets thulium fiber lasers, a newcomer to urology. Currently, the ohmium YAG laser is the gold standard for laser treatments for kidney stones, prostate disorders, and other conditions. Thulium fiber lasers offer several advantages over ohmium YAG lasers. First of all, the wavelength, because water absorption is much stronger at the thulium fiber laser center wavelength compared to the ohmium YAG laser. Also, a larger range of pulse energies, higher rep rate, smaller fiber size, and all of this contributes to higher ablation rates, finer dust size, less retrorepulsion, and overall more predictable treatment endpoints and shorter procedures. And with a bonus, a huge improvement in the size, weight, and power of the laser. Here is shown a typical design and key components of a thulium fiber laser. FBG reflectors are needed to define a cavity, and the critical requirements for these reflectors are a very high reliability, a signal peak power handling of at least 600 watts, a peak power handling of at least 1300 watts for the pump. All of these power handling in the millisecond range. It's a pulse laser. A center wavelength of 1940 nanometer. And these FBGs must be provided typically in 25400 double-clad fiber. Now, fiber lasers are widely used in industrial applications at wavelength around 1 micron, and FBG technology is quite mature. But specific challenges exist at 2 micron for FBGs, and the main challenge is really to limit the heating of the FBGs at 2 micron. Conventional processes that are employed at 1 micron are not suitable for 2 micron. If you use them, then you'll almost certainly end up with fiber fuse type of damage because of FBG heating. Our solution for this application is the MED2 series HPR. HPR stands for high power reflector. The graph on the left shows a comparison of the relative temperature increase of conventional versus MED2 FBGs. We have been able to demonstrate a tenfold improvement in the heating of the component. You can also get a sense of FBG heating looking at the center wavelength drift of the laser as a function of the laser output power, as shown on the graph at the right. You can see that the center wavelength drift is 3 times less with the MED2 series compared to conventional FBGs. So thanks to these results, we can now offer a signal average and peak power handling of 100 watts and 1000 watts respectively, and a pump average and peak power handling of 200 watts and 1500 watts respectively.
Wow.
And so, in summary, the benefits of Direction's MED2 series HPR are a very low heating, which translates into long-term reliable operation, a low insertion loss, which promotes lower cavity losses and lasers that are less prone to self-pulsing, consistent performances, allowing for consistent laser output characteristics, flexibility, which means that we can tailor the reflectivity, bandwidth, type of fiber, etc., to help you reach optimum performances with your specific laser design. And also partnership will work together to quickly iterate and converge to a winning solution so that you can enter the market as soon as possible with your product. So we invite you to contact us today if you'd like to discuss your specific thulium medical fiber laser needs. Thank you for your attention.
Thank you very much, Pascal. Thanks a lot. Can you maybe stop sharing the screen so we go back to the room?
Yeah, sure.
Where the discussion is always better. Very good. Very good. Perfect. Thanks a lot. So Pascal, now a couple of questions about your product. So is it correct that this is now tailored exactly, you brought already, is not only to micron, of course, you are not directly connected to the application, but of course to the wavelength. So that is clear that thulium laser to 2 micron is a bit also the success that is of this product, because basically that is the wavelength you can serve and also the high power level at the same time. So that is the success part. But is it correct that is it mostly for CW and quasi-CW operation? Is it correct?
Yes, that's correct.
So what is it, for example, now, of course, we at Epic, we always want to look at the future, right? So we look at it. This is a fantastic product already. We believe there is a lot of also people in the room that can be interested in this. But what is it that you see that could be a further step? So I have 2 questions mostly. The wavelength and the, let's say, operation mode. So where do you see more possibility to change? So I'm thinking about the mid-IR, because here we have especially one person representing the mid-IR community. And in general, Epic is really strong with this. And so a couple of words about the mid-IR range and a couple of words about the pulse operation. What do you think is a bit of comments about the strategy there, and what is it more important maybe than it is needed?
Yeah, so right now we have a very important product development project to introduce this medical product at 940 nanometer. But in parallel, we have a technology project at Direction, and basically we're looking at we're doing spectroscopy in the thulium band, and we are exploring the limits of what we can do at other wavelength than this one, and there are other applications in the industrial market and defense as well. So we are definitely that's the very first step of a push I would like to pursue in the infrared at Direction. We're really focus on this product right now, but we have activities to enlarge our field of view, I would say.
That sounds great, because that is exactly what you want to hear, right? Already the new plans and the direction. So that means that basically you see more the wavelength is the challenge more than the pulse operation. So the operation mode is something that is now, you're fine with CW and quasi-CW. Is it correct?
And as long as we are talking about pulse duration in the millisecond range and basically gain switch laser at 1940, that's where we have invested the most effort. And if we are looking at Q switch or things like that, we need to work more on finding the limits at specific wavelengths. And so there's still some exploration needed to push the limits for the application.
Yeah, and also, I know what you need. Someone to talk to that tells you we need it, right?
Exactly.
That is what helps the most. We know that.
Yeah, exactly.
So maybe let's see what has Andrea in mind. Andrea for Convergent Photonics, please, you can ask your question. Thank you.
Hi, Pascal. Do you have any possible components that maybe can be used in a holmium region of spectrum, so around 2 micron and 10, 2 micron and 8 nanometer? Have you ever developed any specific component for this kind of lasers?
Good question, Andrea. We have been producing gratings in silica fiber that shows a steep increase in that region of the material absorption. So we can produce gratings still in silica, and I think we'll explore other material as well in the future. But yes, to answer your question, I think we produced gratings up to 2100 nanometer, actually.
Sounds like we are getting there, or you got already there. So maybe you can talk in private on what maybe you can do for Andrea, correct?
Sure, will do.
Great. That's exactly the questions I want to hear and the comments I want to hear. And now maybe Pascal is happy and we can go on.
All right.
Thanks a lot, Pascal, for your contribution. Stay with us. We have still people to discuss other topics.